Okay, I hope I can fill this half hour. I was told that I should speak for 15 minutes, but I have a bit more than this. I can speak a bit slower than now. I made this at a request of the host. I made it very elementary, simple. If you need to have more details about the program, it should be on the website. There have been some delay at our institute in the running of the project, but normally every relevant information should be posted on the website in the course of the month of November. So every little tiny detail you should be able to find there. Now, the project is called EMERISDA, which is the abbreviation of Effectiveness of Methods Against Rising Damp in Buildings. I'm Yves Vanhellemont from BBRI. We are the coordinator of the project. Here you see an overview of all the different partners, 2 Dutch partners and 1 Belgian partner, and several Italian partners, amongst which PMEs. Now, the aims of the project are, as indicated on this slide, to get a scientifically based evaluation of the effectiveness of different interventions against rising damp. I will show you more clearly what kind of interventions exist in reality. And also to define a decision support tool to find the best solution for your rising damp problem in the building in order to achieve, as indicated, the best possible conservation of the monument. I will not go into detail about whether rising damp exists or not. In Belgium we have, unfortunately, a very influential building expert who says that it's a completely invention, rising damp. I can only say, if you think that rising damp is an invention, then you deny totally the effect of capillary uptake of porous building materials, and we all know that this is not an invention, it really exists. If you want to go into discussion about it later on, we can. I have some very strong arguments. Okay, what is this phenomenon of rising damp? As I told you, this is a little experiment that we did in elementary school. If you put a little tube in water, you can also see it in a glass or in these little bottles that you see here at the edge. It curls out the water surface. The smaller the tube, the higher it rises into this tube. You can also do this with 2 little pieces of glass that you put into water. You see the water is rising in between this narrow space. Now, what happens when you do this to stone, which is also actually a material which is completely crossed with a lot of tubes, but very narrow tubes. For bricks, for instance, you get tubes with a diameter of about 1 micrometer, but in mortars, for instance, you find easily tubes that are 1/10 of a micrometer. You also have stones in which the tubes are broader, come to near 0.1 millimeter, for instance. But what happens is, if you put such a material in contact with water, then it can also absorb water. And well, this is how this looks a bit in practice. You get in the first one the contact with the water, then you get the uptake, goes further, and of course towards total saturation you get also air that is trapped into it. It has to dissolve into the water, and after some time, which can take a long time, you get actually what we call total saturation of the stone. Even though I have to mention that in reality with buildings, usually we never reach the situation of total saturation, because of course you have this equilibrium between uptake and evaporation. So usually you end up somewhere in between. How does this look like? Well, this is a very how to say that, pedagogical, I don't know the word in English, example of what does it look like. You get a zone of humidity at the bottom of the building. Usually that is about in the order of 1 meter high, depending on the season and depending about how many humidity is there in the ground. It can be higher or lower, but 1 meter is a good average. Now, does this mean that this only can rise for 1 meter? No, I will show you an example later on. In theory, it might be possible that in some masonries that you get a rise of 10 meters high. Of course, that never happens in reality, because you always have this almost always have this evaporation phenomenon. So in reality, luckily only 1 meter. But don't be fooled, and with that I agree with those experts who say that rising damp doesn't exist. There are humidity problems that show themselves as also that you see a band of humidity or humidity symptoms of some kind, like molds or I don't know what, salts or something like that. It is not always rising damp, of course. Many humidity problems show themselves as rising damp while they are not. So humidity diagnostics is a complex thing which will be also treated slightly in this project. Okay, this is another example. Here you see that this beautiful, more or less horizontal band doesn't need to be horizontal. This is a case of a masonry where you have rising damp, and you see here damage of salts that are, well, salts problems are almost always appearing together with rising damp. Why? Because, well, rising damp usually takes up salts from the ground into the masonry, and the presence of water is actually increasing the damaging effect of salts. Now, there is another program about salts, so I'm not going to go into their domain, but what you see here, what you usually see is that you have a big concentration of salts at the upper zone of the rising damp zone, which is, well, intuitively quite logic, because there you have the evaporation and you get an accumulation of salts in these zones. And here you see the effect of how the salts are actually pushing off the paint layer of this wall. Another example is there you see actually the same phenomenon. Perhaps if you have been in Leuven once and near the wall surrounding the park, you see this beautiful example of rising damp with this salt band where you see an attack of the bricks. And so you see this is not a problem of frost, which also might occur with rising damp, because if this would be frost, then you would see the damage in the lower parts even more, because there the wall's more humid. No, you see it here. So it means this is really a salt-related phenomenon which is in its turn related to the presence of rising damp. Not difficult, of course. There is on the other side a park with all this soil. It rains on it, is being absorbed by the wall, so it's logic that there is a rising damp in this wall. And of course, this is just also a bit aside, examples of hygroscopic salts related to rising damp, which might sometimes take a very irregular shape and sometimes also take the presence of a beautiful wet zone horizontal. I can tell you we did measurements here. This wall is dry, the wall on the right side, wall on the left side also, by the way. This is truly an example of salts. So there is no more rising damp here. But this is an example of how problems that are not rising damp show themselves as rising damp. And it can be even more damaging, like for instance, this is a case of a non-listed building near my place, where you see actually how this rising damp and then also the linked salt phenomena really cause a degradation of mortar. This is after 1 year after the mortar has been replaced, and you see this is a very impressive example of damage. We're going together later on this year doing experiments with our colleagues from the Royal Institute for the Cultural Heritage in Brussels, trying to solve this problem. And the owners are really eager to get a good solution. Frost is another, of course, very dangerous thing that is linked to rising damp, humidity in frost-sensitive materials. Here you get the case of what's the word in English of that? The internal mortar, not the joint mortar, but inside, which is frost sensitive, together with a very dense mortar on the outside, causing being very wet. Frost, it's swelling and it's pushing out the outer mortar. Typical example of frost to buildings. Well, just to illustrate that the presence of rising damp is not something that you really want to have in your building, and that you really need a good solution, because of course theoretically, in Belgium at least the case is, theoretically all buildings from before the Second World War, I'm making a bit of a simplification of it, of course, could be subject to rising damp. They're not necessarily subject to rising damp, but they could be. It is a very general problem. Now, what do you do against these things? A lot of inventions have been developed. A very popular one, and which always works, is a mechanical interruption. You just put a piece of plastic or whatever inside and at the bottom of your wall, and that material is not capillary anymore, and the problem is solved. Of course, that is a very problematic solution, which I will show you later on. Other things are you try to improve the evaporation of the masonry, because as already told, why doesn't the water rise not higher than 1 meter? Usually because you have evaporation. Well, if you improve the evaporation, then you can expect that it gets even lower. That's theoretically a good idea. What the practice means, that's something else. What is done very often in Belgium, but apparently not so often in other countries, is injection of water repellent or pore filling products. I must say these pore filling products aren't used anymore in Belgium for reasons that experience says that they don't really work well. A good solution where you actually don't solve the rising damp, but you solve the symptoms of what are connected to rising damp, for instance, this salt crystallization, is the application of salt buffering plasters, which is also a good thing. Something else you can do also is to change the inner climate of your building. So you don't solve the rising damp, but you diminish or make totally disappear the pathology of the damp, which is in many cases a good solution. But of course you have to have the possibility. It should be adapted to the use of that building. And then you have a lot of other methods, such as I presented more electroosmosis, or we call them electrokybernetic methods. This name is not invented by us, but we see in Belgium and in the Netherlands especially, well, Belgium and Netherlands are two partners in this project, that you have a lot of manufacturers who give these. In Germany they call them Wunderkästchen. I can most easily translate it as miracle boxes that you place against the wall, and they emit electromagnetic waves, and it reduces the humidity in the walls. From a scientific point of view, I think that's an absolute load of, I'm not going to pronounce that word, but of course, as a scientist, you should always be open to every solution. So that's why you say, we'll try this, and we measure it. And if it doesn't work, well, then happy us. And if it doesn't work, then we should go back to school to learn about science, apparently. But, I mean, this will be tested in this project. This is an example of how you could place this mechanical interruption in the wall. This is a very neat brick wall. You see, I don't know, it's very clear, but this is the blade of a saw. So you saw inside the wall. This is what it looked on the other side. So you should be aware that there are no cables or anything. I don't see this happening on this wall, of course, for several reasons. It's very invasive. So the compatibility with cultural heritage is, up to my knowledge, not very evident, even though I know in Belgium there are, in the past, a few decades ago, it has been applied on a, not regular, but it has been applied on monuments as well. So this is a way how to do it. You take this piece of plastic, you put mortar on it, and then you stick it inside. I have no idea how this works, that you get a complete filling of the void that you created, but, well, in theory this should work. But of course, what is in Belgium and also in Italy very common practice, also in monuments, I had the impression that in the Netherlands it was much less the case, is the injection of products into boreholes that you drill into the wall. You inject the product, it being absorbed by the masonry around each hole, and it makes it water repellent, or it fills all the pores. And when you do that, well, of course, your problem of rising damp is solved. But there are many, many different variations about what active molecules that you use. Which liquid do you use to make it, to put it into the wall? Is it an organic solvent? Is it water? Is it a cream? Or is it a liquid? When these active water repellent molecules are inside the wall, do they migrate through diffusion to the pore water, or do they need another liquid in the case of organic solvents, or is it in a gaseous state? It's all different parameters. So as you can see, injection is one word, but there's a completely world of differences behind it. The pressure of injection, is pressure actually necessary? I must say also in the consortium we don't agree, and our opinion is it is not necessary. The opinion of the TU Delft is it is necessary. Well, this is a good occasion to see what is actually true. Perhaps it doesn't make a difference, or perhaps it does. So we can see who's right, we can make a bet on it. But also the humidity content of the masonry is important. I mean, sometimes it happens occasionally that people do preventive injections of walls, sorry. Why do you do that? I mean, it sometimes happens when you want to you have a cave under a building and you want to use it, so you don't want to have all these wet walls. So what they do then, they apply membranes, interior plaster, and they say now these walls are completely dry, now you can use it. But what happens when you do that in a basement? You get a risk that the humidity is rising higher to the ground floor. So what you do then is you actually do preventive injections in the walls while they're still dry at the top of the wall in the cellar. But does every product work for that? No, probably not, but we should test that. I mean, we expect, like for instance, these gel formulated products, that they won't distribute well into the masonry, but that also needs to be tested. This is another example of what to do against rising damp. This is the evaporation pipes of, in Belgium we say the evaporation pipes of Knapen. They are hardly being used in Belgium. They are widely used in France for a reason I really do not understand. But the idea is you make actually holes inside the wall, so you increase the amount of surface in which water can evaporate, and you may expect that it rises slowly, that the waterfront is going down. This is also a very invasive method, of course. It's very visually very visible. I mean, you can see all these little triangles with these grills. And also in this case, you have to cut off pieces of the stone and so on. Is this working? Well, I don't believe in it, and there are also scientific reasons for that, because belief and science are two different things. But okay, let's test it. We'll find out. This is also something which is very, very often used, and it is completely to be avoided. No, not completely, but the application of watertight finishing layers is not an acceptable solution, except when you do site intervention, because what happens when you do that, in the past it has been done regularly, with tiles or with cement renders and so on, you apply this to a wall, and what happens, it cannot evaporate from this side anymore, so the water just rises higher. And to show you that it is a real effect, you have this little street in Leuven. You see this little lady, she is not a dwarf, she is more or less my height, perhaps a bit tinier. But you see this wall here, where you have this cement layer on the outside. This is a sandwich bar for the Dutch speakers here. See, belegde broodjes. So there are also tiles on the inside of this wall, and you see where the front of the humidity comes. It is here. Here you see this salt band, which is not a meter above the ground, because, well, it's about 4 meters above the ground. Just to show you, locking up your humidity is not a solution. Definitely not. Okay, now about the project, because I'm talking a lot about rising damp and its pathology. What is happening now in the project? What has been done now is actually the inventory of the different types of interventions, together with a first screening about what we may expect from it based on literature and so on, but also what intervention will we try out in reality, because as we later see, we will actually carry these out both on sites and on scale models. Also very important, because of course if we want to see if a method against rising damp is efficient, we should have a good method about how to evaluate this. Now, we also all know that these things exist, they are a bit scattered, we have all different philosophies that we already found out when we compared our methods to the methods of our Dutch colleagues or the methods of the Italian colleagues, which is very enlightening, I must say. So we come to an agreement about how we test this, because we have to test both sites in Italy and in Belgium. There are no practical sites in the Netherlands. And we have to do this always in the same way. These, as already told, will be posted on the website emerisda.eu. I invite you to go there, but not too fast, because now there's already something on it, but it's a bit too empty now. So wait a month, and then it will be very complete. Sorry, yeah. Now, what also needs to be done on short notice is a selection of sites where we want to do these techniques. We want to actually try this out in real life, on real buildings, which is not so evident, of course, because always the question we get from heritage owners about, yeah, but you do that, but you say you're going to try something out, so there is the risk that it doesn't work, and perhaps the side effect, which are also very logic questions. So we have to convince people, and of course we have to, that's our responsibility, that we just don't do whatever what, and then we make a building crumbling. That is of course not the case, so we have to be careful, but we select these sites on their sensibility. I will present you one. I mean, there are more than well, the San Marco Basilica in Venice is for instance selected as a possibility. Then of course also selection and execution of techniques to be executed in these buildings, that has to be selected. There's a lot of selection in this phrase. Why? I mean, if you list up all of these different possibilities that I just mentioned, I mean, I have an astronomical list of all possible interventions. If you want to, well, this wall wouldn't be enough to test all of these things on. So, okay, we have to make a selection, of course. There is also a part, the execution of small-scale models. Why? Because there we can master the test parameters. So, what we do actually is we have real sites, we have scale models where we can control all the parameters. The results of those should be linked, calibrated if you want, to each other. And actually what we're also going to do when it comes to injection products, the BBRI has established together with Royal Institute for Cultural Heritage years ago a method to test injection products, very, very little small samples. And what has never been done is actually to get the link between what we measure in laboratory and what we measure in real life. Is actually what we put in these test reports of these products, is this actually good? Can you really extrapolate what we do in laboratory to reality? This is a very good occasion to actually test this. Okay, an example of one of these test sites. This is in Antwerp, which is a very nice neighborhood. This is the Felix warehouse. I have been contacted by them already years ago because I have a big problem in the cellar. It is a very beautiful, so this is a warehouse from the end of the 19th century. So it's the harbor. Now you only see these yachts, but 100 years ago there were other types of boats that were there. This building is executed with cranes in the central lane, and this was actually used to store goods. Now, of course, this is next to the harbor, and you want, when your goods are stored, that they stay dry. So what it has been done, it's a very intelligent construction, I must say. There is a cellar, which looks like this, beautiful, impressive cellar, which was used for nothing. Just an empty space between the place where you store your goods and the water. The groundwater level is only 1 meter below the ground here. So you dig a hole there, and 1 meter lower you find the water. So the foundation of this building are in water. Now, this has been standing there for more than a century. Now, a few years ago, this building has been changed in function. Now it is the archive of the city of Antwerp, which is a big archive because Antwerp is a big city and an old city. But of course, you know, architects say, a very nice empty space. What can we do with this? So now, of course, there are installations for all kind of things, and there is also a bar, and they say, what a very beautiful, because it's very spacious. We want to do little concerts in there, exhibitions, and so on. So now you know what happens. You have this cellar, which has always been almost closed. Now it's being opened, and what happens? You see actually, here you see how the mortar is degrading. In a few years, it has been degrading more than in the century before that. So it's a, well, big problem. You see, I don't know if you see this little wall. So you can actually, if I go up again, these are the lines of these vaults here, of these arches. And you go, this is actually the line of sand that is falling off these walls. You also see the efflorescence on the floor. This is actually a brick floor. Regularly they vacuum it so that you see it again, and then, well, 1 year later, 1.5 year later, or a year later, it's all covered in sand again. This is of course not a very good thing, because on the longer term this will cause this building to completely be crumbled. Now, as you can see, these cellars are very big. You only see a small portion of it. There are numerous of these pillars, and now they ask, what can we do with it? Now we said, okay, empty this basement, but it is of course not a solution. So what is a good solution? A part of the, or even a big part of the solution, will be to stop the amount of humidity in these columns, because that amount of humidity is high. We measured it, it is very high. So the city of Antwerp is very much interested what is the best way of reducing the humidity in these columns. Will this cause the problem to disappear completely? Well, with a bit of luck, yes, even though I have my doubts, but the problems will be reduced strongly when you don't have a supply of liquid water anymore in these columns. Just to show you how big this, they have this lighting system with aluminum housing of the lights, and it's actually being attacked by, well, I'm not a chemist, but I mean, it should be the effect of lots of sodium sulfate on aluminium. I didn't know that this could happen. I thought aluminium was very strong and inert metal. Well, it is not the case apparently. And this is only the situation 2 years after the restoration, so it goes fast. Okay, I thank you for your attention. If you have any questions, you have